Hello, uh, class of 705. Um, by popular request, I wanted to make a video specifically dedicated to reviewing carbohydrates, since several of you asked questions about that on um, the exam 3 review session. Um, so the definition of a carbohydrate is a molecule that has the formula CnH2ON, approximately. Uh, some molecules like glucose, which is C6H12O6, fit this perfectly. Um, Other molecules that are generally considered carbohydrates do not, such as sucrose, which is C12H22O11. It's like two. It's a glucose plus fructose, but you remove a water, so it doesn't quite fit the ratios. Um, and so one important um, class of distinction between different kinds of carbohydrates is aldoses and ketoses. The reason that we need the reason that carbohydrates to fit the CH2ON formula perfectly um, need these carbonyl groups either as an aldehyde or a ketone, is that if they were fully saturated with hydrogen, so like if this was a hydroxyl instead, then this carbon atom would have a total of 3 hydrogens bound to it. Two, much like this one, it would have 2 hydrogens and then an OH for a total of 3 hydrogens. Then each of the others would have 2 hydrogens, so the ones on the end would each have 3, and all the others would each have 2. And so the total number of hydrogens would be 14, which is more than twice the number of carbons. And so you need this partially oxidized carbon to actually get um, the C6H12O6 formula. And so this is model of glucose, and this is model of fructose. And in order to better keep track of these carbon atoms, they're numbered in a systematic way. You always start numbering from the side of the molecule that has the carbonyl group. So for aldoses like glucose, this is easy because you start numbering from the carbon with the aldehyde group. This is carbon 1, then you go up to carbon 6. For ketoses like fructose, all the ketoses we'll deal with in this class will should have the the carbonyl group in the second position. So the carbonyl group is clearly on one side of the molecule or the other. So you just start numbering. You start numbering carbon 1 at the end of the chain that's closest to the carbonyl group. So this would be carbon 1, and then the carbonyl group becomes carbon 2, and you go down the chain. Probably the only carbohydrate that we'll have to deal with, in which case it is not clear which side is closer to the carbonyl group, will be dihydroxyacetone, because it's a triose, so it has 3 carbon atoms, and the carbonyl group is in the middle, so it's equidistant from the 2 end carbon atoms. Dihydroxyacetone is symmetrical, though. It's achiral. It has no carbon atoms with 4 different substituents on them. And so the 2 carbon atoms at the ends can be considered equivalent. And so there's no, since there's no distinction between them, it's not really important which one is carbon atom 1 and which one is carbon atom 3. This distinction does become important if you're looking at the form of dihydroxyacetone that occurs in glycolysis, dihydroxyacetone phosphate, in which case this carbon atom with the phosphate group is numbered 1, and the other one is numbered 3. So many sugars have the same chemical formula. For example, glucose, galactose, and mannose are all C6H12O6. But lots of sugars are isomers of each other. Um, and a special type of isomer is called an epimer. And an epimer is where you have two sugars that differ at exactly um, one chiral carbon. So for example, if you look at galactose and glucose, um, their structures are identical except that at this carbon that I've circled in red, which is carbon number 4, in glucose, this carbon points down, and in galactose, this carbon points up. And so galactose and glucose are epimers of each other. Similarly, glucose and mannose they also differ by one carbon atom. So in this carbon atom that I've circled in blue, which is carbon number 2, in glucose, the hydroxyl points down, and in mannose, the hydroxyl points up. So glucose and mannose are also epimers of each other. However, mannose and galactose are not epimers of each other because they differ at 2 positions, carbon 4, which points up here and down here, and carbon 2, which points up in mannose and down in galactose. Another important point to note is that even the same sugar, such as galactose, can exist in multiple forms. So there's the linear form seen in the Fisher projections, and there's also multiple cyclic forms. So for hexoses like galactose, glucose, mannose, fructose, many hexoses can exist in multiple forms that are cyclic. And forms that are cyclic and have 6-membered rings, like this, are called pyranoses. And cyclic forms that have 5-membered rings, like this, are called furanoses. And so you prefix the word pyranose with the name of the sugar. So for example, this one is called galactopyranose because it's a pyranose made out of galactose. And it's D-galactose, so it's D-galactopyranose. And pyranoses and furanoses can also have multiple conformations at carbon number 1, which is called the anomeric carbon, because it's the one that has the for aldoses, it's the one that has the aldehyde group, and so galactose and glucose and mannose are all aldoses. So for them, the carbon 1 is called the anomeric carbon, and anomers are a special type of epimer where they differ by the conformation at carbon number 1. But as I'll discuss later, these groups can actually interconvert under just in aqueous solution without the aid of any kind of enzyme. They can interconvert rapidly in a process known as mutarotation, which I will talk about later on. And so these 2 forms, the alpha and the beta, with the hydroxyl group pointing down and the hydroxyl group pointing up, are not, you can't isolate them. You can't like make a solution of only alpha galactopyranose or only beta galactopyranose because they interconvert very rapidly. And so alpha is always the term referred to when the hydroxyl group is pointing down, and beta when it's pointing up. And for ketoses, the anomeric carbon, so the anomeric carbon is always the one that has the carbonyl group on it. So for ketoses, it will not be carbon 1, it'll be carbon 2. And so because so many sugars are isomers of each other and differ only at whether like hydroxyl groups point up or downwards, as well as the D and the L configuration, it's important to understand the stereochemistry of sugars, like how the atoms are oriented in space. And so the nomenclature that we use, the DL and the L nomenclature, was coined by a scientist named Emil Fischer in 1891. He was studying a molecule called glyceraldehyde, which I have a model of it right here, and it's also the molecule that's shown on the screen. And so it had been observed that a solution of that there were 2 different forms of glyceraldehyde, and the solution of one of them would rotate light to the left, and one of them would rotate light to the right. The one that would rotate light to the left was given the designation levorotary, and the other one dextrorotary. And so Fisher knew that the structure of glyceraldehyde had to be something that looked like this, but he had no idea if this form with the hydroxyl group on the left was the one that rotated light to the left, or if it was the form of the hydroxyl group on the right that rotated light to the left. So he took a wild guess, and he had a 50% chance of being right. He guessed that L-glyceraldehyde. He guessed that the form with the hydroxyl group on the left was the one that rotated light to the left, and vice versa. And although he only had a 50% chance of being right, but he was correct. And so he gave it wasn't shown that he was correct until the 1950s, when they used X-ray crystallography to actually solve the structure of glyceraldehyde. But in the meantime, he called this configuration of atoms the L configuration, and its mirror image the D configuration. And so the way to determine if a particular carbon atom in a carbohydrate is in the D or the L configuration is you simply take the sugar has a carbonyl group, either an aldehyde or a ketone group. You point that upwards, and then the second step is to orient the carbon atom that is chiral such that the groups that are pointing up and down are going away from you into the page, and the ones that are pointing left and right are coming out of you. These are shown by the dotted lines and the solid triangular lines, respectively. And then the third step is to look at which side the hydroxyl group is on. If it's on the left, then it's the L configuration, and if it's on the right, then it's the D configuration. And so in the model that I have here, if I orient it the same way, so take the aldehyde group and point it upwards, and then make sure that the aldehyde group and this carbon atom at the bottom are both pointing at me, or at me and away from you, the observer. Then which configuration is this molecule in, D or L? So this one is in the D configuration because the hydroxyl group is on your right side. And for sugars that are more complex, like I have a model of glucose right here, which is currently in the cyclic form, convert it back into the linear form of glucose, like so. Okay, so yeah, so for molecules of carbohydrates that are more complex, like glucose here, the way to determine if they are D or L is you point the aldehyde or ketone group upwards with respect to the rest of the molecule. The aldehyde or ketone group is for all the sugars that we're looking at will either be in the 1 or the 2 position, and so there will never be any ambiguity as to whether the as to which way to point the aldehyde or the ketone group, because it'll always definitely be in one half of the molecule. The only exception is dihydroxyacetone, because it's a 3-carbon sugar with the carbonyl group in the middle. But dihydroxyacetone is not chiral, and so it doesn't have a stereo configuration anyway. But you point the aldehyde or the ketone group upwards, um, and then look for the lowest carbon atom that is chiral. So for glucose, carbon 6 has 2 hydrogens on it. I haven't put them on the structure to make it a little simpler to look at, but there are 2 hydrogens here. So this one does not have 4 unique substituents, and so it is not chiral. But carbon 5 has this upper half and this lower half, which are different, and then a hydrogen and then a hydroxyl group. And so carbon 5 is a chiral center. And so you look at carbon 5 and you make sure that both the top and the bottom groups are pointing away from you. The hydroxyl is on one side and the hydrogen is on the other side, and they're both pointing towards you. And then just ask, which way is the hydroxyl group pointing? And so for glucose, the hydroxyl group is on the right side, and so this is also a D sugar. And every naturally occurring sugar that we'll study in this course is also a D sugar. So one of the trickiest things in carbohydrate chemistry, at least conceptually, is converting between a Fisher projection and a Hayworth projection. And so there's actually a fairly simple way to do it. And the simple rule is you take the you take the Fisher projection and you flip it onto its right side. And then if a hydroxyl group is pointing downwards when the Fisher projection has been flipped onto its right side, then it's pointing downwards in the Hayworth projection. If it's pointing upwards, then it's pointing upwards in the Hayworth projection. So 2 is pointing down, 3 is pointing up, and 4 is pointing down. We get to 5, there's another rule, is 5 does not have a hydroxyl group, but the rule for whether carbon 6 is pointing upwards or downwards is that if it's a D sugar, carbon 6 will point upwards. If it's an L sugar, carbon 6 will point downwards. So if all you want to do is learn the rule, that explanation will suffice. If you'd like to know why it is that, or where this rule comes from, then I'll show you using this model of D-glucose, the same molecule that I'm depicting here on this slide. So in D-glucose, of course, it's an aldose, so we have this aldehyde group up here, and this becomes carbon 1. And so in the Fisher projection, the rule for the Fisher projection is the aldehyde or the ketone group should be on the top half of the molecule, and then whatever groups are pointing upwards and downwards will be pointing away from you into the page, and then whatever groups are pointing on the sides should be pointing towards you out of the page. So I'm just going to bend this molecule into a conformation in which that's true. And in order to make that conformation true, I will need to bend it into this ring shape. I'll explain why. Because so right now I've placed so this is the top of the chain. So as long as I keep the molecule like this, the carbonyl group will be pointing upwards. And now if I go to carbon, so this is carbon 1. The one that's connected to it is carbon 2. And so if I look at carbon 2, the hydroxyl group is pointing to the right. And then if I go to carbon 3, you can see that the groups that are pointing upwards and downwards are still pointing out of the page, away from you, towards me. The hydroxyl group is pointing towards you. And so it's because I bent this molecule into this ring conformation that like the 2 carbons above and below will always be pointing away from you, no matter how I turn this ring, because the ring is convex, like the the carbons on the top and the bottom will always be further away from you than the carbon that's pointing straight at you, which is why it's helpful to bend it into this ring conformation. So if I'm looking then at carbon 3, hydroxyl group is pointing to the to your left, and then for carbon 4, it's pointing to your right, and for carbon 5, it's also pointing to your right, and then carbon 6 is not chiral, so it doesn't have a conformation. Now, since I can just rotate this ring to go from one carbon to the next, and I never flip the ring over like this, you can see that all the hydroxyl groups that were pointing to the right should have been, they will all be on one side of the molecule once the actual molecule gets converted into a ring. And all the hydroxyl groups that were pointing to your left will be on the other side of the molecule once it gets converted into a ring, because this is although I've just bent the molecule into the ring, this is the actual plane in which the molecule will lie once it chemically gets converted into a ring. And so all the groups that were on the right side, they'll either all be pointing up or down, and the group that was on the left side will be the opposite of the groups that were on the right side. So the question is, will the groups on the right side be pointing up, or will they all be pointing down? And the answer is they'll be pointing down, and that doesn't come from some law of the universe. It just comes from the convention of how we draw the Fisher and Haworth projections. And the reason is, so if I flip the convention for drawing the Haworth projections is that you put carbon 1, so carbon 1 is this one, you put carbon 1 on the, just trying to figure out how to angle this, put carbon 1 on the right side like this, and then you put carbon 2 here and carbon 3 here. And so just the way that the Haworth projection is drawn, the only way that I can satisfy that arrangement is if then all the hydroxyl groups that used to be on the right side of the Fisher projection are now pointing downwards, like that. So that answers the question for hydroxyl groups on carbons 2, 3, and 4. But what about the hydroxyl group what about carbon 5? How do we know that when we form the ring, how do we know that carbon 5 will be attached to carbon 6 pointing upwards, or will it be attached to carbon 6 pointing downwards? And so the way that we know that is, so because carbon, this is a D sugar, and so the hydroxyl group for carbon 5 was on the right side, so it's pointing down now. And in order for, and this hydroxyl group on carbon 5 is going to be the one that has to attack carbon 1 in order to form the ring, because the two carbon atoms that are linked through the oxygen atom in glucose are carbons 1 and 5. And so in order to, if it starts pointing down like this, the hydroxyl starts pointing down like this, in order to get the molecule into a conformation in which this oxygen atom can attack carbon 1, I will need to hold it. I need to hold it so that you can see what's going on. I will need to rotate this bond until the oxygen atom is in a position where it can attack carbon 1. And as you can see, in the process of rotating the oxygen atom upwards, I've also rotated carbon 6 upwards, so it's pointing upwards in the final molecule. And so if instead this hydroxyl group had been pointing, Yeah, if instead the hydroxyl group on carbon 5 here had been pointing upwards because it was an L sugar, then when I rotate this bond to get the oxygen atom into the position, you can see that carbon 6 rotates downwards. And so for L sugars, the carbon 6 will be pointing downwards, and for D sugars, I'll convert it back into a D sugar now. For D sugars, the carbon 6 will be pointing upwards. And so once I form this bond, um, oops. So I form this bond again, I'll start by deprotonating this hydroxyl group, and then I attack carbon 1, form this tetrahedral intermediate, pop off the, break the double bond and convert it into a single bond, and then reprotonate the oxygen. Now, the uh, the glucose molecule has been transformed into its um, cyclic or into its six-membered ring, or also called pyranose structure. And so this is now known as glucopyranose. So I wanted to talk about the phenomenon of metarotation and anomers that result. So glucose, um, when it's in solution, can exist in two primary forms. So the cyclic form of glucose, which is a six-membered ring, and six-membered sugars with six-membered rings are called pyranoses. So this is called glucopyranose. And so the pyranose form is the most abundant form of glucose in solution. It's much more stable than the linear form. And so the linear form only takes up about 0.02% of glucose when it's in aqueous solution. And the cyclic forms take up most of the rest. And so the pyranose forms can come in two different kinds. So one is called alpha pyranose, which is where the hydroxyl group is pointing downwards. And the other form is called the beta form, where the hydroxyl group is pointing upwards. The beta form is slightly more stable. So at about 64% of glucose is beta glucopyranose, and about 36% is alpha glucopyranose. But these forms can interconvert very rapidly. And so it's not like one molecule, it's not like every molecule makes a choice of whenever it, it's not like one molecule makes a choice that it sticks with for the entire duration of its existence as glucose. And so these molecules can interconvert rapidly, and I'm going to show the mechanism of how they can do that using this model of glucose. So here it's in the linear form with the aldehyde group on carbon 1. And the mechanism of how it actually converts into the pyranose form is that first, I'm looking at carbon 5 here. The hydroxyl group on carbon 5 will get deprotonated, and then this oxygen atom with its negative charge and its lone pair will attack carbon 1. Now this forms an intermediate, be a tetrahedral intermediate, and because carbon doesn't like to form 5 bonds, it's going to break one of the bonds involved in the double bond of the oxygen. And this bond is going to be replaced with this oxygen atom, and then this oxygen will leave with its lone pair, and then that'll get reprotonated with a hydrogen atom from some hydrogen atom, some proton donating group in solution. And so this will form the cyclic version of glucose, pyranose version. And then adjusting its conformation here to get all the groups, get all the other groups equatorial. You can see that this, once you get all the other groups to be equatorial, then this hydroxyl group is pointing upwards. And so this is beta glucose. Now, in order to reverse the process, I just have to deprotonate this hydroxyl group. And then the lone pair on this oxygen atom reattacks carbon 1, which causes reattacks carbon 1, which causes the bond here to break and the oxygen atom to leave. So this bond reforms and this oxygen leaves, and then it gets reprotonated. So it's in the linear form again. And then then if it gets deprotonated again, it can reattack. And the decision of whether the glucose molecule becomes alpha or beta just depends on which of these. Well, it'll for this model it'll depend on which of these two single bonds that are making up this double bond that I choose to break. But in the actual glucose molecule, where double bonds are not actually two single bonds, it'll depend on which side of the aldehyde group this hydroxyl attacks. So here I've attacked this side again, and this forms beta glucose. If I break this bond again and reform the linear version, and then this reattacks, and I break the other bond this time, then this will form alpha glucose with the hydroxyl group pointing down. And so this is the mechanism in 3 dimensions of how beta-rotation happens. And another, beyond the realm of simply monosaccharides, once you start building them into 2 carbon units, or to 2 sugar units of disaccharides, or into multiple sugar units of oligosaccharides, and build those up into polysaccharides, it's important to understand how glycosidic bonds, which are the bonds that form between sugars, are named. So glycosidic bonds are a type of ether bond. It's called an ether because ethers are molecules in which you have a carbon atom, you have an oxygen atom that is single bonded to 2 carbon atoms. That's known as an ether. So glycosidic bonds are ether linkages, and they're named based on the 2 carbon atoms that they connect in the different sugars, as well as whether they are pointing up or down. So let's see. Let me so for let's see, hide my video panel so you can see this better. So in this type of glycosidic bond, first we look at the 2 carbon atoms that it connects. So it connects carbon 1 of this molecule of glucose to carbon 4 of this molecule of glucose, and so it's known as a 1,4 bond. And for this carbon atom number 1, it's pointing downwards, so the hydroxyl group is in the alpha configuration. If it were pointing upwards, it would be in the beta configuration. So this is known as an alpha 1,4 glycosidic bond. As an example of, and this type of bond is found in starch, including amylose and amylopectin, and also in glycogen. And here's an example of a beta 1,4 glycosidic bond where the hydroxyl group of carbon atom 1 is pointing up. Instead, this kind of bond is found in cellulose, and these 2 different geometries of bonds give starch and cellulose very different properties. glycosidic bonds can also be between carbons other than 1 and 4. In glycogen, for example, you have alpha 1 6 and alpha 1 4 glycosidic bonds. So here on this carbon atom, this is carbon atom 1 of, of this sugar. It's pointing downwards, so this is an alpha bond, and it's connecting carbon atom 1 of this one to carbon atom 6 of this sugar. And so this is an alpha 1 6 glycosidic bond. This one is an alpha 1 4 glycosidic bond. And so combining alpha 1 6 and alpha 1 4 glycosidic bonds is what enables one glucose molecule to attach to two others through its 4 and 6 carbons and create these branched chains that are important for quickly assembling and breaking down glycogen. So with that, that concludes my video on carbohydrates. I wanted to wish you good luck on the exam, and feel free to reach out to me by email or on Piazza if you have any more questions before the exam. Take care and have a good day.